In this video, I am going to build on our earlier video and start our discussion on the normal distribution model. Let X here represent the height of an adult male in the United States. Well, there is a particular height that is called the average height. So if it's average, I'm going to represent it as mean, the mean height. And it tends to be around what? For adult males, around 70 inches. It is very common in the population, so I'm going to draw a line, a vertical line, as high up as this. And I'm going to note that not all adult males in the US have that same height. Some people are taller, the basketballers. And how frequently do we encounter them in the population? I'm going to draw another vertical line, but not as high as the previous one, because basketballers, people who have that height of basketballers, are not as common in the population. The same goes with those who are shorter than average height. They are also not as many. So I'm not going to draw a line as high as the previous one that I drew for the average height, which is the most common height. So if I were to connect the dots here, the dots being the top of that vertical line, I would have a picture that looks like a floating ghost. This picture represents the normal distribution model. In other words, the normal distribution model is very suitable for quantities that are one, measured, e.g., the heights of adult males are measured, they are not counted. So you cannot use the normal distribution to represent quantities that are counted. Only quantities that are measured, weight, height, and so on, are examples of such. And it must be a random variable or a variable that has a particular value that is very, very common in the population. And of course, that very common value is not the only value. There are other values that are spread away from that very typical value. And if it meets those conditions, the normal distribution model will be a very good fit. From the picture we've drawn here to represent the normal distribution model, you will notice that if we were to cut the normal distribution model right at about the line in the middle where you have the average, then you have about two approximately equal halves. In other words, we say that the normal distribution curve is symmetric right around the point where it has its mean in the middle. Another characteristic of a normal distribution is that the mean, the median, and the mode are very close to each other. And so it's a unimodal distribution. Then there are these points where the curve, the probability curve, tends to what? To fall faster. Those 2 points are called the points of inflection, and they tend to occur if from the mean, the average height in the middle, or the average value in the middle, if you take one standard deviation forward from the mean and one standard deviation backward from the mean, you arrive at the inflection points. It is not surprising that the total area under the normal curve is equal to 1, since the bars here represent relative frequencies or probabilities. And so the sum of that total area is equal to 1, aka because it represents probabilities. And those are pretty much the major ideas. Whenever we draw or sketch the normal distribution, the line that represents the curve never really touches, never really touches the horizontal axis. It will come as close as possible, but it never touches it. And so we say that it's a form of asymptote. Let's take another illustration here, or another example here. In this context, we're interested in the serum total cholesterol for males who are 20 to 29-year-old. Data collected on this variable, which is the serum total cholesterol, shows that it follows a normal distribution, and the mean is 180 and the standard deviation is 36.2 for the population, based on data obtained from the National Health and Nutrition Examination Survey. Based on this information, we are required to draw a normal curve with the parameters labeled. First of all, what is the variable being observed for males who are 20 to 29-year-old? That would be the serum total cholesterol. I'm going to represent that as X, and it's represented as X as a variable because it will vary from one 20 to 29-year-old male to another. Well, according to data observed or obtained, it is obvious, it has been reported rather, that the mean, the most common observed value for the serum total cholesterol measurement is 180. So that will be the number in the middle. And we expect that for other members in the population, there will be a spread, there will be other values. On average, how are other values spread away from this mean value in the population? That is given by 36.2, which is one standard deviation. So from 180, if I were to take a step of standard deviation equals 36.2, I'll arrive at 216.2. This is a point, this is an inflection point. The other inflection point would be starting from the reference point 180 minus 36.2, the standard deviation. I'll arrive at the other inflection point, which is 143.8. So these 2 points are the points of inflection. So I have the normal distribution here for the serum total cholesterol. Now, based on this representation, an individual with total cholesterol greater than 200 is considered to have high cholesterol. The requirement of this problem is to shade the region under the normal curve to the right of 200. Why? Why to the right? Why not to the left? Let us see. Let us bring down the normal distribution curve that we sketched earlier. The very common value being the mean, which is 180. And of course, we want to locate other values. In particular, there's a threshold here, which is 200. And 200 should be to the right of 180. So I'm going to locate it somewhere here on the horizontal axis and draw a line here. And I'm interested in those whose total cholesterol is greater than 200. That'll be somewhere here to the right. So the area to the right there under the normal curve represents the region that is required in this question. And of course, it will be to the right because only values to the right of 200 exceed 200, since we read from left to right. In our probability finding, how can we interpret this area? The first interpretation is that the proportion or the fraction of those in the population of interest, 20 to 29-year-old males, who have high cholesterol, greater than 200, is this value that has been provided to us, 0.2903. In other words, another way to state that is that the probability that a randomly selected 20 to 29-year-old male has high cholesterol, that is, cholesterol greater than 200, is 0.2903. That is based on the provision of this question here that says that suppose the area under the normal curve to the right of x equals 200 is of size 0.2903. How provide two interpretations of this result? So a usual question we get at this point is, how did we get this 0.2903? There is a calculator that we're going to be using in StatCrunch in order to compute this, and I will show you that. So Right away, if I go to StatCrunch, if I go to Stats, I go to Calculators, I'll go to a normal distribution calculator, click on that, and you see a sketch of the normal distribution. Well, it has two parameters, the middle value, which is the mean, and the standard deviation, which represents the average measure of spread away from the mean value. The mean in this question was 180, and the standard deviation is 36.2. And we're interested in the area to the right. To the right, that will be above. Above what value? Above 200. And if I hit complete compute, then I have 0.2903. So this calculator helps me to calculate the size of the red area. And so back to our work page, we have this piece right here. All right. Now, still talking about the parameters of the normal distribution, that is the two major levers of this distribution that are very useful in describing that distribution completely, namely the most common value, the typical value in the middle, which is the average, the mean, and the other value called the standard deviation, the population standard deviation, which tells us on average how other values are spread away. The key question we ask is, what are their purpose, or what is the purpose of each of these parameters of the normal distribution, which are the mean and the standard deviation? One, for the mean, it simply represents how far to the left or right the center of the normal distribution is. Take for instance, if I have two normal distributions who have the same standard deviation, but their means are different. The one with the lower mean will be shifted more to the left than the one to the right, than the one with mean of 3 whose distribution will be further to the right. Why is that so? Well, since we list numbers from the smallest to the biggest, from left to right, it makes sense that smaller numbers are on the left and bigger numbers are on the right. And so the number with an average of 0, which represents the center value, will be centered more to the left as compared to the one which has a higher mean, and so will be centered more to the right. Another thing to quickly highlight this importance is a graph here, which I've provided here. You will notice that for both distributions, both normal distributions, the purple one and the blue one, or normal distribution A and normal distribution B, both of them are centered at 10. So the mean is equal to 10. Well, we have been told that one has a standard deviation of 3 and the other one has a standard deviation of 2. Standard deviation is a measure of spread from what we have learned earlier in this class. So that means that the bigger standard deviation indicates that we're pointing to a distribution that is whose values are more spread out. So looking at the picture, which of the distributions is more spread out? B or A? Obviously, it's B. So B is such that the standard deviation is bigger because it's more spread out as compared to standard deviation A, or the purple one, whose values are more closer or clustered together. Here's another example. Two normal distribution curves are provided below. Which distribution has a smaller standard deviation? Which one has a larger mean? I have been provided with the inflection points and the mean. The mean in this case is 151. The step between the mean and the first inflection point, that is the size of one standard deviation. So what will be the standard deviation in this case? This is 203. That is the gap between 203 and 151, and that is equal to 52. Whereas for normal distribution t, the mean is 120, and the step between the mean and the first inflection point or the upper inflection point is the standard deviation. The standard deviation then will be 140 minus 120, which is 20. So we now have the information that we need to determine which distribution has smaller standard deviation. Obviously, it is distribution T that has what? The smaller standard deviation. And which one has a larger mean? That is, which one has the larger value in the middle? That will be that will be normal distribution S with a mean of 151, which is definitely greater than the mean of 120 here.